Hello and welcome back. This is the 9th in the series of presentations on system requirements analysis. This is the latest, or as of 2021, the last paper presentation I made at the International Symposium. This is from 2018, Formalizing Requirements, Verification, and Validation. Based on some work I was doing with Bob Noel my last couple of years at Boeing. And so we decided to put this together in a presentation for the International Council on Systems Engineering at the 2018 Symposium. What I'm going to talk about is listed here. What do we mean by requirements, verification, and validation? How do these relate to correct and complete requirements? How do these relate to what's in the INCOSE guide regarding to writing requirements, regarding characteristics of requirements? How do we measure these things? What do we mean by correct sets of correct requirements? And then some conclusions. And in the presentation, of course, I gave opportunity for questions. And if you want to submit questions, you can submit them via the YouTube channel, or my electronic mail address, or LinkedIn. So what do we mean by requirements, verification, and validation? So the INCOSE SE Handbook, I'm using version 4. Verification is talked about in 4.9. Validation is talked about in 4.11. Requirements are mentioned, but don't say how this is done. We have tumbled to this idea of verified and validated. Validated relates to what the stakeholder needs are. So this is viewed from the perspective of the various stakeholders. Verified is more specific with respect to being able to check with respect to requirements. So we've decomposed verified requirements, meaning they satisfy the parent requirements and they conform to standards for all requirements, whereas validated requirements satisfy stakeholder needs and there's no unnecessary ones. So we think about validation in terms of operational use and top-level requirements that are validated versus needs. And then the lower-level requirements are verified versus the parent requirements and standards. And then at each architectural level, these yield a correct set of correct requirements. And really that's what we mean by verified and validated, is correct set of correct requirements. And this paper formalizes and decomposes these definitions and provides measures for being able to demonstrate that verified and validated requirements are equivalent to correct set of correct requirements. In other words, each individual requirement is correct and the set is correct using all definitions of correct. This idea of correct and complete arises from the industry standard ARP 4754A, which is used for commercial airplane development. The INCOSE Guide to Writing Requirements excuse me, has 14 characteristics, which can be implemented or interpreted as providing validation and verification criteria. We viewed this set as having a number of problems. It's not concise. The characteristics are not disjoint. There's a lot of overlap. And given those two things, we thought it begged some simplification. So we've attempted in this table to map these characteristics from the guide into our 4 criteria. And some of them map directly, like necessity, essential capability. So that clearly maps to necessity. Several of the other ones having to do with how a requirement is worded map to the idea of verifiable. So appropriate and ambiguous, singular, they got verifiable here, conforming, complete, and comprehensible are collapsed. And so we think this set of 4 is actually easier to use and easier to measure and prove out when one is evaluating requirements. So in this slide, I'll be talking about exactly how these map. So verifiable is the first thing we always check for, and you see that in the 2015 paper, how we measure requirements quality based on its verifiability. Because if it's not verifiable, you're probably not going to be able to determine any of the other characteristics because there's some degree of lack of clarity or ambiguity. So we associate verifiability with these other characteristics from the INCOSE guide: appropriate, unambiguous, complete as individual and as a set, singular, verifiable, conforming, and comprehensible. So it has to be understood in order to be able to make any of the other analyses come true. So complete, this was actually first described in my earlier work in 1998 and the working group project in 2004, has been emphasized throughout this series of presentations, that a requirement has to be both necessary and sufficient to be complete. And the idea of necessity associates, maps directly to the C1 necessary characteristic. Sufficiency, however, includes several other things, that it's complete at an individual level and it's complete at the set level. In other words, the requirements are sufficient to satisfy the parent requirements and needs and able to be validated. And there's some overlap here with some of the verifiability criteria, as I've indicated here. So this is why I say the INCOSE 14 characteristics are not really disjoint. Feasibility includes an assessment of whether the requirement can actually be implemented as described. And I'll talk about each of these characteristics in some detail, but the INCOSE guide properly realized and documents that feasibility is both at an individual level and at the set level. Consistency or lack of consistency could be a problem and means there's conflict, and therefore not all the requirements can be satisfied concurrently, or there's just some inability to be validated. So I'll go through the 4 characteristics one at a time, but you can see what our suggested mapping is of the INCOSE guide characteristics to our 4 requirements characteristics for validation. Correct and complete. Each requirement and the set are correct. So correctness inherently includes completeness, since an incomplete set of requirements cannot be correct. That's a type 2 error for omission. So that's why we talk about correct set of correct requirements, and that implicitly includes the idea of completeness. So the first idea of verifiable, that the requirement is sufficiently clear and complete to be able to prove that it is needed, that is necessary, satisfied, and feasible. And if it's ambiguous, then one or more of these may not be able to be determined just simply because it's ambiguous. So this is why we always start with, well, what does it say? What does the requirement say? And can we determine what it means? And is each requirement complete with respect to, for example, a requirements pattern or template that says you've got to have these elements like an observable function and clear inputs and outputs and a condition statement and performance attributes and so forth. In other words, you can compare a requirement statement to a defined pattern as one means for determining completeness and therefore verifiability of that requirement statement. Necessity means that the parent requirement or need cannot be satisfied without this requirement. In other words, if we delete the requirement, we will fail to satisfy some parent requirement or need. And that's the easiest test. Well, let's just remove it. What you may find, and what we have found, is you can delete a requirement and still satisfy a parent requirement because there's a duplicate somewhere. So at least one of those is unnecessary, as an example. The sufficiency criterion means that if this requirement is satisfied as it's worded, and that harkens back to the idea of verifiability, because if it's not verifiable, I may not be able to determine these things. If the requirement is satisfied, then the parent requirement or need will be satisfied. That's a deterministic assessment, although that sometimes that may be in combination with other requirements at that same level, sometimes allocated to other entities in the architecture. But without this requirement, the parent requirement, with this requirement and all others that are associated with it, then we can deterministically prove that we can satisfy the parent requirement. That is, this requirement is sufficient to satisfy the parent requirement. And finally, the feasibility criterion, that each requirement can be satisfied within the program constraints with acceptable risk. And these requirements, these characteristics we assert are disjoint, they don't overlap, they are concise, and they're complete. That is, they're necessary and sufficient to determine that we have a correct set of correct requirements. So the measurable characteristics are done by evaluating these. And so correctness is a combination of feasibility, necessity, sufficiency, and verifiability. And this Venn diagram shows what you might have, that verifiability would be the largest set, that all requirements that I'm going to attempt to examine have to be verifiable before I can probably assess either necessity or feasibility or sufficiency, just because there may be some degree of ambiguity. But I have to have the intersection of these things. That is, every requirement has to satisfy verifiability, necessity, feasibility, and sufficiency in order to be correct. By implication, taking the contrapositive, then if any requirement is either not feasible or unnecessary or insufficient or unverifiable, then it cannot be correct. We score verifiability using our requirements quality measurement that I talked about in the prior presentation, a scale from 0 to 4. It's a quality attribute of how well the requirement is stated according to the pattern and its elements and the degree to which each element satisfies the criteria. Necessity is scored as a binary. It's either necessary or it's not. In other words, if I cannot satisfy the parent requirement without this requirement, then it's necessary and it scores 1. On the other hand, if I could delete it, then it scores a 0 because it's not necessary. Sufficiency is also a binary attribute. Either the requirement is sufficient to satisfy the parent or it's not. And sometimes we have to look at the combination with other requirements at the same level that are decomposed from a common parent to assess the set of child requirements with respect to the parent. These two criteria lead to what we have historically called requirements completeness in my papers going back to the 1990s. And finally, feasibility is measured essentially as a risk or an issue. So it can get graded from 0 to 1. 1 means it's feasible with manageable risk. 0 means it's infeasible, and it wouldn't matter how much money you spent trying to satisfy it. So let me go into these in a little bit more detail, how we get there. So verifiability is checked first if the requirement is unclear or it's missing elements. cannot necessarily be determined to be either necessary, sufficient, or feasible. And we use the Boeing templates from our prior presentation. Each element of the requirement arises from the architecture and the related performance analyses. So we have traceability, which is a necessary element of necessary and sufficient, and the ability to assess the sufficiency. So we use the requirement quality measurement from the prior presentation. It's graded from 0 to 4. This includes identifying the type and identifying the elements of the requirement, and then scoring each of the elements, the who, what, the who, shall, what, how well, under what conditions, with respect to the particular requirement type. So for the example, functional performance type, the agent shall function in accordance with the interface output with performance, and then an optional clause, and timing upon event trigger in accordance with interface input while in condition. So we can evaluate any example requirement with respect to this pattern and say, is the agent properly identified? Do we have the mandatory characteristic? Is the function observable at the output? What is a constraint on the interface? Is there a performance attribute associated with the function? And is there timing characteristic for a triggered event? And is there a constraint on the trigger? And there's a larger statement of conditions, so we know when this thing has to be done in general, like environments or states. And each of these characteristics can be evaluated with a how well quality to get us to our somewhere in our 0 to 4 score. So that's what we mean by verifiability. It conforms to a pattern we've established and has all the essential elements with adequate characteristics. The necessity criterion flows directly from the INCOSE guide, C1. The requirement defines an essential capability. So there's that mandatory description, characteristic, constraint, or quality factor, meaning the parent requirement or need cannot be satisfied without this requirement. This is really the easiest one to test for. For example, if I have a set of requirements, a parent requirement A and subordinate requirements B, C, D, and E that all trace to characteristic A, and if, for example, I don't have B, and that means I'm not going to get A, then B is necessary for A, because I can't have A if I don't have B. So if I deleted B, the B requirement, I wouldn't satisfy the parent requirement. And that's how I know that B is necessary for A. So I've validated B with respect to A. And the measurement here is binary. We want a yes in order to keep it. And if it's no, then it's a 0. Note that certain needs may be derived from other than parent requirements. In other words, it may be, especially at the top levels, that the set of parent requirements is actually incomplete with respect to all possibilities. And this was discussed in the 1998 and 2004 papers, building on the idea of anomaly handling from the 1995 paper. So when we do failure analysis, safety analysis, anomaly handling, we may identify additional conditions that actually aren't reflected in the parent requirements, and therefore derive needs for additional requirements to ensure deterministic behavior under all possible conditions. These requirements aren't necessary to satisfy the parent requirements, but they are necessary to ensure a complete and deterministic system. Sufficiency means that satisfying the child requirements ensures that we satisfy the parent requirement or need. So this is slightly different from simply tracing and say, oh yes, this child requirement is related to the parent. What this means is the union of contributing child requirements is deterministically sufficient to satisfy the parent requirement, and failure to satisfy any child requirement causes the parent requirement to fail to be satisfied. So if parent requirement A decomposes into child requirements B, C, D, and E, then if I can show that the union of these requirements deterministically satisfies the parent, then I would say B, C, D, and E are sufficient to satisfy the parent. And so I have to examine these requirements together by some analysis to show that A is satisfied. And if there's some set of conditions that's missing with respect to A, then I may need another requirement, or I may need to alter one or more of the subordinate child requirements. If B intersection C and intersection D and intersection E implies A, then we say that these are collectively sufficient to satisfy A. And we would note that sometimes child requirements for a parent may actually be distributed over multiple subsystems. So one would have to examine the totality of the decomposition and allocation of the parent to all the child requirements in order to assess the child requirements as a set with respect to sufficiency to satisfy the parent requirement. Again, the measurement is going to be binary. Either we satisfy the parent requirement sufficiently or we don't. Feasibility is an assessment of whether we could actually implement this requirement. And it includes the feasibility of the individual requirement, feasibility of the set, consistency or lack of conflict. For example, you might have two requirements addressing the same topic, such as weight, that have different numbers. Well, then we have an inconsistency, and depending on how they're worded, either they may be infeasible or one of them might not be necessary. But if the requirement is feasible, then the requirement does not violate the laws of physics, because it doesn't matter how much you need it. If it violates the law of physics, it's infeasible. You cannot have it. Or it violates laws or regulations. You would not be allowed to build something that violate or operate or maintain something in a certain jurisdiction if it violated those laws or regulations. So it's infeasible, even if it's from an engineering standpoint, quite tractable. If it conflicts with other requirements, then either that requirement or the set of requirements is infeasible, because they cannot, both requirements or the set of conflicting requirements cannot be satisfied concurrently. That's what we mean by conflict. And the last element is not a hard boundary here. It's, does it incur excessive program risk? In other words, it may not be absolutely an issue, but it may not be feasible with respect to the program as it is defined. So we might have to say, we could do that, but not on the schedule or with the budget that we have. These characteristics can actually be tested individually, one at a time for each requirement, and as a set. So any particular requirement might be infeasible, and it may be the case that a set of requirements where each requirement is feasible, but collectively they're infeasible because they can't all be satisfied concurrently because of conflict, or cannot all be satisfied concurrently because of program risk. There's not enough schedule, there's not enough budget, whatever the problem is. So feasibility can be checked sometimes independently of the parent requirement, but we do need to check it with respect to other requirements at the same level. So we don't require the parent-child relationships, and the measurement now becomes a degree of risk. If it's infeasible, it's an issue. We know it can't be satisfied for some reason. If it's a 1, then we say there's no risk, and we can move on. So if we apply these 4 characteristics over a set of requirements, then what we have is a statement about necessity, sufficiency, and verifiability with respect to each requirement, and also a statement about feasibility across all requirements for a particular entity. So we may also have to include requirements from other elements as regard the sufficiency check. So there's a lot of cross-mapping. Requirements databases, requirements management tools can be very useful for helping us in this, but someone is still going to need to do the analysis to check for individual feasibility, combinational feasibility, and sufficiency with respect to the parent requirement. As I said, feasibility has to be checked at the set level for consistency and conflicts and excessive risks. And so we have, in order to have a correct and complete set, we need each individual requirement to be verifiable, feasible, necessary, and sufficient. And the set of requirements also needs to be feasible with respect to the program. So if we have correct sets of correct requirements, then we have realized verified and validated requirements according to the definitions in the INCOSE SE Handbook. So conclusion, satisfying these 4 disjoint characteristics of verifiable, necessary, sufficient, and feasible is necessary and sufficient to verify and validate requirements individually and as a set, and then to establish a correct set, that is a correct and complete set of correct requirements. And by making measurements, we can understand where we are. So we've identified these measurements for each characteristic, so we understand where the deficiencies might be and point to whatever improvements are necessary. So I thank you for your time. Thank you for participating in this journey. As I said, all these papers that are presented at the INCOSE Symposia over the years are available in the Wiley INCOSE Symposium library. That's free for INCOSE members. You can go to incose.org, INCOSE.org, to either become a member or find the path to the library. You'll see there the written papers, not these presentations, but the written papers that have the details behind what I presented. If you'd like to send a note to me, ask a question, you can get to me through LinkedIn or ResearchGate, or if you have my electronic mail address, I'm not going to give it to you right here, or pop a comment on the YouTube channel and I'll get notified about that and I can get back to you. So thank you very much for your attention. Watch this channel. I may be posting some additional presentations from other places where I've given talks, but this set are the sets of papers, presentations I've given at the various INCOSE Symposia. Thank you for that opportunity. Thank you for participating, and I wish you all the best in your requirements development activity. Thank you very much.